Hello and welcome back to this organosilicon class, where we are talking about how we can produce industrially very useful and very important compounds on silicon as well as the corresponding carbon part, that means the alkyl part attached to it. So, these organosilicon compounds can further be modified by the use of some other groups or the introduction of some other functional groups, and those functional groups are industry wise very important because they are giving you some other important molecules like that of your rubber or the corresponding resin molecule. So, like that of your application like that alkyl acyl oxy material type of thing or the alkyl material, now we move to some introduction of the oxime function. So, introduction of the oxime function to the silane backbone. Silane backbones are nothing but, you can remember it nicely, that these are the corresponding hydrocarbon type of thing, where we know that the hydrocarbons are nothing but you can have the carbon and hydrogen attached to that a particular skeleton. Now, if you replace this particular group by silicon, you get SiH4, the corresponding analog of methane. And then slowly if you can have a mixed variety, that means one part you can have the alkyl function, that means the methyl, ethyl, propyl group functions, and other part is simply ending up with silicon and hydrogen or silicon or the halogen or silicon or the other functional group. Now, we take a very simple molecule like that oxime functions, how we can introduce that oxime function to the silicon oil or the silicon polymer unit. So, this particular one, if we take the organic structure, what has been shown over here is nothing but your butanone oxime. So, it is basically a 2 butanone oxime. So, is one side is a skeleton is basically a 4 carbon skeleton with a 1 carbonyl group. So, this particular carbonyl group, when it has been converted to oxime function, so the butanone is nothing but CH3CO CH2 CH3 group. When you have this CO function, and that CO function can be converted to your oxime function, that is also well known. We know that how ketones are converted to the oximes through the use of hydroxylamine NH2OH. So, the direct refluxing of that hydroxylamine in presence of a drop of acid type of catalyst, that means a drop of hydrochloric acid, dilute hydrochloric acid or 1:1 hydrochloric acid can give rise to the corresponding formation of these oximes. So, this why we are talking about some oximes basically, because this particular compound is a corresponding oxyaminosilane or amino-oxysilane, that means amine function is there, one oxygen function is there, and we get the silane. So, methyl tributanone oxyaminosilane is formed by reacting trimethyl trichlorosilane, that means already you have the CH3 function SiCl3 with 2 butanone oxime. What happens basically? Because we should know also that how we get the product, because you may be asked also that what is the reaction product of methyl trichlorosilane with 2 butanone oxime. So, you should know how this particular material, that means the oxime function is there in your hand, how reactive it is to a particular type of chlorosilane. So, your chlorosilane is nothing but CH3 SiCl3. Then we are utilizing with HOX, that means the corresponding material what you can have in your hand and is abbreviated as HOX. What is that HOX? Is the H is nothing but your oxime hydrogen, and the remaining part including up to NO is your oxime function. It can be a very simple oxime, that means hydroxylamine it can be also, because that when you have C double bonded O, and that C double bonded O can be converted to a oxime, and that oxime we all know that oximes are very useful in terms of its caprolactam chemistry, in terms of its nylon 66 formation, because these oximes can be reorganized and reframed in terms of its corresponding amide backbone, and that amide backbone can be useful for different types of polymeric material, the nylon 66 type of material, because that we can have one is acid and another is the amine, and acid amine condensation will give you the corresponding amide bond. Now here we are going for this ox, because this ox is the oxime function including up to NH, that means NH so corresponding NO double bonded C, CH3, C2H5, the whole molecule itself you have. So is almost a little bit higher than that of your room temperature reaction, which is at a less than 60 degrees centigrade, giving rise to the replacement of 3 SiCl bonds by this oxime functions. So what we get, again our intention is very simple, that we will try to reproduce the material in terms of the attachment of the oxygen of the oxime function. Oxime functions are NOH, so that NOH will be there, then hydrogen will go away from that oxime functions, that hydrogen will go and it will be occupied by the Si group. So CH3 SiOX whole 3 we will get, and the corresponding free oxime group, because only 3 are being attached and we are utilizing with 6 of them, because you require the corresponding protonation of those groups which are in the deprotonated form. So these protonated groups, that means HOX, that means when H is attached to it, you get is that HOX. So HOX and its hydrochloride salt. So 3 of these, because the 3 chloride groups are coming out, chloride ions are coming out from SiCl bond breaking process. So the attachment on the silicon center of the oxime functions in a particular form will give a new type of material and is utilized as cross-linking agent. Again, it can go for cross-linking between the polymeric chain. In silicon silanes also, that means the further improvement of those silanes. Just now what we have seen, that we can have the silane material in which the acidic reaction products are undesirable, because we are blocking the corresponding acidic function, that means no H you can have from the acidic proton from the corresponding material, the silicon silanes, which are removed only, that means everything is blocked, not by the formation of your SiCl bond or SiH bond, it is everything is blocked by the oxime NO groups to the silicon center. Then we move to some amidosilanes. Now we realize it that we can have large number of organic functions or organic functional groups which can be attached to those silicon centers. So remember by name basically, because once you are asked to know the material, by knowing the name you will be able to understand that what type of silane it is. So if you have the amide function attached to the silane molecule, it is the amidosilanes. You have the corresponding agene groups, that means the further nitrogen functions, that means the nitrogens are there. Some extra aja functions or the nitrogen functions are attached to the silanes, which are known as silagens. So N,N-bis trimethyl silyl urea. So we know urea, and urea is basically a carbon based compound. So you have the CO function attached to NH2 function is your urea. Now you can have the trimethyl silyl urea, that means your corresponding groups will be substituted by the silicon groups, is obtained by reacting hexamethyl disilaagene. So that means silagenes are using with urea. So this is your hexamethyl disilaagene. So disilaagene, you can have the silicon ends on the both sides, and you have the in between you have the NH. So the aja function, aja means not only the pure nitrogen but the NH function is there. So you have the NH function and both the two ends, basically it is nothing but your type of dimethyl type of amine. So dimethyl amine is nothing but you have NH function, at one end you have the methyl function and the other end you have the another methyl function. So instead of methyl you have now trimethyl silyl function. So trimethyl silyl at one end and another trimethyl silyl function at one other end, basically giving a typical amine function is a secondary amine, which we know that dimethylamine or the diethylamine, where you have two alkyl groups on the both sides of the nitrogen, making it R2NH. Similarly, it is Si2NH. And Si2 is again, as the Si2 group is a bulky one, because the silicons are not SiH function or SiH3, they are again SiR3. So these are then reacted directly with urea. So is direct reaction of this reactive material, which is nothing but your hexamethyl disilaagene, giving rise to some important molecule where we are trying to substitute this particular one. That means you have now the CO function intact, nitrogen, that one NH group is there, because this NH group is already, we know that this NH group is there. So this NH can be now protonated through the protons of the urea molecule. So, what we get basically, that means this will remove as ammonia, this NH is removed as ammonia, and this NH function that on the urea side left and right can attract the attachment of trimethyl silyl groups. So, trimethyl silyl groups, it attached to NH group of the urea. So, it will be trimethyl silyl NH. So, trimethyl silyl NH, twice of that with the CO giving you that particular desired molecule. So, the starting material on which we are adding urea molecule. So, hexamethyl disilogen utilized as a agent for introducing the protective groups. So, the protective groups are bulky one, bigger one, which are nothing but your trimethyl silyl groups. So, trimethyl silyl groups are very useful protecting groups, because we want to improve the corresponding quality of the material, the quality of the silicon rubber. So, this group basically repels water molecules which are hydrophobic in nature. So, introduction of Me3Si group in the silicon rubber material or the silicon corresponding silicon polymeric backbone is basically changing its hydrophobic nature, and it is basically the introduction of the hydrophobizing agent group or the nature of the particular filters, and found by reacting of the trimethyl chlorosilane with ammonia. So, sometimes if we react instead of urea, if we can react with the ammonia also. So, on the ammonia also this particular silane group can be introduced and give the corresponding reactive material, which can be very useful, and when they can be polymerized we get some very useful material for industry. So, when you have NH3, the reaction course is little bit different, but you have again some kind of secondary amine function, because the amine function now what we can have is around this NH function. So, NH, Si, CH3, CH3. So, how we get this material? So, this material we can obtain it from the trimethyl silyl chloride with the reaction with ammonia. So, you get it. So, you see that this organosilicon chemistry is so rich that you can have this material, you can have the starting trimethyl silyl chloride react with ammonia, you get some compound, and that you react with urea to get some other useful compound. So, the reactivity pattern of these organosilane compounds, organohalosilane compounds are always important to know, because the basic reactions we can formulate it out to material wise if we can try to improve the corresponding material chemistry of the silicon as the silicon organosilicon compounds. Then if you try to retain the hydrogen which is originally there in SiH4, say the silane molecule itself, and as we have told you that this particular hydrogen can be substituted by the alkyl function to give the corresponding organosilane compounds where less number of silicon hydrogen bonds are present. So, one such example is now that if you try to retain those hydrogens on the silane backbone, we will be getting some organohydrogen silanes or organohydrosilanes. So, organohydrosilanes are formed by products in the direct synthesis of dimethyl dichlorosilane. So, instead of monomethyl, if we can go for the dimethyl one, so the corresponding one as the corresponding organic hydrosilanes are formed as the byproduct. Similarly, this can also be utilized as precursors for organofunctional silanes and hydrogen containing siloxanes. So, siloxanes we can have, and if we are not able to remove all the hydrogens from the silane backbone, that means not we are able to destroying the corresponding silicon hydrogen bonds entirely or completely, we can have some remaining compounds where the silicon hydrogen bonds are present. Then what is that hydrosylation reaction? That means you have silicon, you have hydrogen, and you have the further organic part. So, that particular reaction you can have. So, what is there? Therefore, that like that of your reaction which can be added basically. So, if you have a compound, you can have on one end you can have halide groups, that means the corresponding chloride or bromide groups attached to the silicon. Mostly these are all chloride functions, or some alkyl groups, that means the carbon silicon bonds are there, but at one end the functional moiety of these reactions are that you have to have a corresponding molecule where you have the silicon, at least one silicon hydrogen bond in that particular molecule. So, hydrosilation reaction is that you introduce that particular one to a corresponding addition, that means silicon is attached to one of the carbon and hydrogen is giving for the corresponding hydrogenation of the double bonded structure, that means you can have carbon carbon double bond structure. So, basically instead of addition of hydrogen, we know that how hydrogen is getting added to the double bond of the organic molecule. So, that is known as hydrogenation reaction, but when silicon as well as hydrogen both are attaching to that particular center, we get the corresponding hydrosilation reaction. And the important interest is that compared to that of your hydrogen addition to the double bond is that the silicon already have some other groups attached to it on the other side. That means only we are talking about one of the silicon hydrogen bond, but on the left hand side you can have more number of silicon carbon or the silicon halide bonds. So, it is still functional. You can replace those groups one after another to get another new compound. So, what we can have these R groups attached to this particular vinyl function. Again we are talking a vinyl functional group, that means CH double bonded CH groups and corresponding one also some vinyl epoxy groups attached to that particular compound with the help of a platinum based catalyst. Then we see that the different types of functional groups we can introduce. So, different types of organofunctional silanes we can have, we can make them a very interesting class of molecules based on silicon, which we can have these groups as not only R and X, but also we can have Y. So, it is not that our life is getting more and more complicated, but stepwise we should know that we can introduce R group on silicon, because the basic molecule is the same that of your methane, that means CH4, it is SiH4. So, when simple silane is there, that means it is a tetrahydrosilane, that means all are hydrogen attached to the silicon, satisfying is tetravalent or the +4 oxidation state. We introduce R, we get some organosilane compound. Though we introduce, we get the corresponding X, that means the corresponding other groups or the halogens are there, we get some X. Then we can also have some other functional groups based on that particular X, or other functional groups which are not of other type, that means which are not of X type, you can have the Y function. So, when X is the silicon functional groups, silicon attached to those functional groups, that means you can have alkyl or alkaline function as R and R prime. Then you can have the corresponding Y is also there, R is alkyl or alkaline function, X is the silicon functional groups attached to that particular silicon, that means it can be your X, Cl itself also, and then Y is the functional group in terms of your NH2, CN, Si, and the well known and well discussed still now is your vinyl function. Then this alkenyl silanes. So, alkenyl silanes you can have the alkenyl functional groups, then R prime is the double bonded one, alkenyl function, not alkyl function. So, when you have the alkenyl function, the reacting with hydrogen containing silanes with ethyne in the presence of a platinum catalyst that we have just now we have seen, that it can react for your SiH group for the presence of the corresponding hydrogen in it, that means the hydrogen groups will be attached to that particular double bond, will be converted to a saturated backbone. So, when you have the CH double bonded CH1, we call it as the vinyl silanes. So, these vinyl silanes are utilized as cross linking agent for making polymers, because the vinyl groups are susceptible for your polymerization reaction. As we all know, we have the vinyl polymers, because the corresponding polyvinyl chloride, we know that the polyvinyl chloride you get the corresponding PVC compounds, the polyvinyl chloride based polymers we get. So, vinyl groups attached to the silicon get another variety or another type of polymeric compounds, and as the functionalization agent for the silicones. So, if we have a silicon rubber itself, then we can further functionalize in terms of the corresponding vinyl groups attached to it. So, is X is in your hand, R is in your hand, SiH groups are there, so that you can introduce Y as some other group. So, Y, if we try to have the Y as the corresponding alkaline function, that means CH double bonded CH, you use directly with acetylene. And again a platinum based catalyst or the platinum based compound will be useful for this direct conversion. of this particular reaction. So, your silicon will be attached to that particular acetylenic function, making that particular one as the corresponding vinyl function. So, one of the hydrogen from SiH will be added to that other end of the carbon, and one end will be attached to your silicon. So, what you get? You have the silicon attached to one carbon, and the other end of the carbon will be reduced by the hydrogen already present with that of the previous silicon center. Organoamino silanes. So, amine function how we bring, and these amine functions what we have seen that simply Y function is your NH2 function, and again it is basically another useful compound is still now we know that the addition promoters and in making different types of useful composite material. So, the composition of this is that you have the corresponding organoamine silanes and you get a corresponding composite material. Then haloorganosilanes, that means you have still the halide groups attached to it. So, silanes with organohalone groups are utilized as precursors in the production of other organofunctional silanes and as component of different reactive silane products. So, when you have an active groups present in it, whether you have X already present as the alkyl group or Y, that means you have a different reactive silane molecules or the silane products you have, which can further be modified in terms of its ability for polymerization or any other type of reaction. Then introduction of sulfur in silicon chemistry or the silicon rubber chemistry is that the mercaptan group can be introduced, and those mercaptan groups can give rise to something where we get basically the corresponding mercaptosilanes or the sulfidosilanes. So, mercaptosilanes means you have the free SH functions. So, already you have that reactive one that like that of our thiol molecules, and sulfido groups you have the corresponding sulfide groups or the ether groups, thioether groups, that means double bonded S functions are there. So, when it linked with sulfur, because we know that the typical rubber material or the polymer material can be utilized for vulcanization with the introduction of sulfur, because the sulfur as a good sulfur source can be utilized for a cross linking material. But now if we are able to introduce that particular sulfur to the silicon material or the silicon backbone, that can also be very much useful for a different types of cross linking material. So, again it is like that of our previous cases, it is addition promoter or is a vulcanization additives in the rubber industry. So, a different types of silicon rubber we are utilizing, and that silicon rubber can have already that have the sulfur thing, and that sulfur can be utilized for your cross linking material. Now, we move to silicons, that the basic silicon molecules what we can have. So far we have talked about the silanes and all other substituted silane varieties. Now, we will talk about the silicons. So, like that of your acetone, what we know that the silicon is also the corresponding variety when you have the corresponding carbon centers are replaced by the corresponding silicon center. So, the silicon atom each linked to one or more organic groups via carbon silicon bonds are linked to one another through oxygen atoms also to provide a straight chain. So, you have one end you have the carbon or the alkyl function attached to the silicon, and in between you have the silicon oxygen silicon bond. So, like that of your acetone you have the carbon double bonded oxygen, but here silicon oxygen silicon bond is basically your silicon material because it is a polymeric molecule. So, siloxane has the general formula. Siloxanes are basically that corresponding oxygen is there. So, that particular oxygen is the repeating unit. So, OSiH2 which can be repeated in SiH3 backbone. So, you have all you have is that silicon attached to your hydrogen, and you have the silicon oxygen bond. So, two types of bonds are present. One is the silicon hydrogen bond which will be very reactive, and another is the most stable silicon oxygen bonds within this particular material. So, you see that if we look at this formula in the structure, so structurally silicons are nothing but polyorganosiloxanes. So, siloxanes you have silicon oxygen bond present, and which are your repeating unit? Sil-oxane. So, sil is the silicon and oxane is the oxygen. So, silicon oxygen part, that means the building block is your silicon oxygen group, and when that silicon oxygen group is getting repeated one after another with some other functional groups at the periphery or at the other end of the molecule, polymeric molecule rather, we get a polyorganosiloxane molecule, and we consider this as the siloxane material. And this N can vary a lot. These N values can go from say 1 to 14,000. So, molecular weight of these materials are very high. So, we get basically a rubbery material. So, that rubbery material is not even oil, it is not even fluid, it is basically rubbery material when the molecular weight is very high. Sometimes these are very useful because compared to other carbon analog of this polymeric material, your property wise these silicon materials are far superior compared to your organic carbon based polymeric material. So, what we see now, we said classify their properties, and once we know the properties very well, we will be able to compare those properties with that of our carbon based molecules. So, those carbon based molecules what we can have can be compared with this silicon based polymeric material such that we can have certain advantages for this silicon based rubber material or silicon polymers. So, basically these are nothing but your silicon polymers. So, what are those properties? We have a huge list of these properties what we can have. So, these properties basically we can have in terms of its stability. The first thing what we can consider is stability. So, it has a very high temperature stability because your silicon oxygen bonds are very stable. If we consider that okay, we can have also some silicon carbon bonds and silicon hydrogen bond, but the main backbone is formed out of your silicon oxygen bonds and silicon oxygen bonds, what we know these are very stable system. So, you have a high temperature stability for these compared to your carbon analog of these polymers. It is stable to the oxidation, that is very difficult to go for its typical oxidation reactions, because the carbon related molecules or the carbon hydrogen related molecules or the hydrocarbons are susceptible for oxidation in some drastic condition, because the carbon and hydrogen will be very quickly oxidized to the corresponding carbon dioxide and water, which we all know. The hydrocarbons when oxidized in presence of oxygen or in presence of air, it basically produces carbon monoxide, carbon dioxide and water molecules. But if we talk in terms of the corresponding oxidation for your this material, that means the silicon based polymer or the silicon rubber, we cannot consider this as the corresponding oxidation is so facile. So, thing is that the facile reactivity of the silicon rubber we may not have. So, we can resist the corresponding oxidation in terms of its aerial degradation of the material. So, that is why these materials are far more superior compared to its corresponding organic or the carbon analog as of the polymeric material. Then weathering is also very difficult to have, that means with time, with age, the degradation of this silicon based material is less compared to its corresponding carbon based material. It has also the very high hydrophobicity, that means it will repel water, because water is always a difficult thing for any material, even if you go for some paint material based on the silicon oil, such that you have a building material, and the silicon oils are nowadays very much useful while we making the paints, that we will consider in our lateral classes. So, where we consider the paint material, inorganic paint material, because this will be a very useful application of the inorganic paint material. So, if your hydrophobicity is less of that silicon oil or material, what we are utilizing for dissolving the dyes and the pigments, for making the paint, for even painting anything from the building to the corresponding automobile industry. So, we can change or we can introduce or we can increase the hydrophobicity of the material through the introduction of SiMe3 type of material or the group, or SiR3 type of group, such that the hydrophobicity is such that we try to increase the hydrophobicity of the material. So, you modify those silicon centers through the attachment of more number of alkyl groups or bigger alkyl groups or the bulky alkyl groups attaching to your silicon center. So, you can have different types of structures, because you can have different types of cross linking, different types of chain arrangement or the chain linearity. It depends on the structure for their foam destabilizing agent, foam stabilizing agent also. If we use them as the foam material, then you can have also the corresponding usefulness as adhesive material. You can have also the electrically non-conducting material, because these are all polymeric material, and these polymeric materials are not very useful for giving electrical conduction or the thermal conduction. Even for the electrical conductivity, it can reduce the corresponding conductivity and it can function as a good insulator. Then it can have some thin film you can make out of those polymers or the rubber material. So, silicon polymer based films you can have, which can retain the corresponding gas or the vapor, or sometimes you can pass selectively some of the vapor or some of the gas molecules. So, you can monitor or you can change and you can modulate the corresponding permeability of small molecules. So, the small molecule permeability can be changed or can be improved through the introduction of the different types of functional groups in all these polymeric materials or the silicon material. Then physical properties can change little with the temperature. So, is the corresponding one. So, it can withstand the temperature rise or the temperature decrease, and is also sometimes the physiologically compatible, that means the biocompatible material. So, different types of prosthetic grooves, different types of body material, different types of living materials nowadays we are making, where it can follow the biomechanics, it can follow the corresponding biocompatibility of these materials. So, the silicon implants basically. We can port those silicon rubber or silicon jelly type of these materials for the typical silicon implants in our body also, without going for any harmful effect. So, is also very much physiologically compatible in nature. So, next day what we will be talking about something, the remaining part of the silicon material, what we can have, that how people have discovered it and how people consider this silicon material will be useful industrially as well as its different applications. Okay. Thank you very much.